Hello, and welcome to the second part of our ongoing series of videos examining how to successfully leverage the SOSA technical standard. I'm Mark Littlefield, Director of System Products at Elma Electronic. In this video, we'll be diving deeper into the SOSA OpenVPX slot profiles that we covered in Part 1 to better understand how the definitions captured in the SOSA standard promote the various attributes called out by the standard, like interoperability and replaceability. Specifically, we will be looking at 5 general topics. We will start with some details of the utility plane. Next is the protocols for the data plane, control plane, and expansion plane, followed by some connectivity rules for plug-in cards. We'll look at XMCs and overlays, and we'll wrap up with an overview of amps. So, let's dive in. The VITA65 utility plane is composed of 2 regions, the P0 connector, which we see on the right, plus a portion of the single-ended pins of the P1 connector that we see on the left. SOSA uses most of these signals and ports just as they're called out by the OpenVPX document, with a few important exceptions involving the VS2 and VS3 voltage rails, the plus and minus 12 volt aux pins, and 2 of the slot profile defined pins in the P1 single-ended pin region. Specifically, the SOSA technical standard mandates the use of only the VS1 12-volt DC power rail for main plug-in card power, so the VS2 and VS3 rails are unused. SOSA has also redefined these 2 pins as nuclear event detection, or NED and NED return. And 2 of the slot profile defined pins in the P1 single-ended region are defined as a maintenance port. Looking more closely at these changes, as I said, only the VS1 12-volt DC rail is used for main power. VS2 and VS3 are to be unused and must be no-connects. Note, however, that 3.3 volt aux is required, as it is used solely for the chassis management functionality that is required by the technical standard. We will be looking more closely at SOSA system and chassis management in a later video. NED and NED return are defined on P1 connector pins D4 and D6. The exact implementation of these pins is not defined by the standard, only the pins are assigned for this function. The maintenance port is intended to be a serial console port for an onboard processor. Note that while it is a UART and is essentially RS-232, it is defined as using LV-CMOS voltage levels, not the normally higher RS-232 levels. Note also that some profiles, like the 14.6.11 profile, define a second maintenance port. This was added to these profiles because it is not uncommon to have 2 separate computing resources requiring consoles on these profiles. Taking a slide from our first video, we see the details of 2 3U SOSA slot profiles. Remember from that video that we have 3 critical communications planes defined: the data plane, the control plane, and the expansion plane. However, this does not describe what communications technologies or protocols are implemented on these pins. While other ports also have various protocols defined, for this video we will focus only on these 3 primary communications ports. VITA65 defines many communications protocols for the various ports found in the slot profiles defined by the standard. The SOSA technical standard constrains those to a much smaller set of protocols to enable better interoperability. The data plane is limited to 40G base KR4 and 100G base KR4, 10G base KR and 25G base KR by partitioning the 4-lane data plane into single-lane ports, 1000 base BX and 1000 base KX for certain profiles, and PCI Express Gen 2 and 3, again only for certain profiles. Note that this list is heavily biased towards Ethernet solutions, which offers auto-negotiation, further easing integration of different components. Note also the alphanumeric codes listed for each protocol. These codes are used by the AMPS construct, which we will discuss later. The control plane is further constrained to only Ethernet protocols, specifically 10G base KR and 25G base KR, and in certain profiles, 1000 base BX and 1000 base KX. The expansion plane allows for a wider selection of protocols because, unlike the data plane and control plane, it is used for off-chassis links as well as slot-to-slot links. The protocols allowed on the expansion plate include PCI Express Gen 3 and 4, and in a few profiles Gen 2, Aurora, Serial Front Panel Data Port, GP LVDS 15, and 40G base KR4 and 100G base KR4 for certain profiles. SOSA also has rules that define how plug-in cards can implement protocols on these ports. Specifically, if any port is unused, it must be unconnected or otherwise electrically benign. In addition, designers are not permitted to repurpose pins for functions other than what the standard defines. If the board designer wants to implement only a portion of a defined port, like only implementing 4 lanes of a PCI Express on an 8-lane expansion plane, they must strictly follow the VITA65 rules for partitioning ports. One important rule is that port usage starts at the lower numbered lane or port and counts upward. XMCs are an important part of the SOSA technical standard. Not that the standard defines much in the way of specific rules or definitions for XMCs themselves, but because XMCs provide a way to bring specialized outside connectivity right to the plug-in card. However, there are certain expectations that drive the few rules relating to XMCs, including that mezzanine map pins are not routed to other backplane slots. This in turn means that XMC pin routing must go somewhere else, which in most cases means outside of the chassis. Mezzanines are chosen to match specific platform I/O needs that are not expected to change over time, or at least very often. It is probably intuitively obvious, but deployable backplanes will be designed with a specific mezzanine in mind, routing its signals as needed. And lastly, carrier card technology insertions can be accomplished by moving the mezzanine to a new carrier before inserting it into a chassis, with the rules in the standard ensuring that the signals map correctly. The standard only has 2 slot profiles which map mezzanine I/O to the backplane, one 3U and one 6U. Beyond this, the rules are relatively loose to encourage a wide market for XMC cards. One rule that is quite strict doesn't actually apply to XMCs, but to the carrier board. It is obliged to route I2C connections to the XMC site so the XMC can integrate into the system management infrastructure if it offers the necessary sensors. One last item to note about XMCs is overlays. The SOSA technical standard defines a small set of XMC overlays for both the 3U, called Type A, and 6U, or Type B, profiles. The thoughts behind the overlays were to define a few relatively simple XMC mappings that SOSA identified as commonly being needed. For 3U, the overlays define a GPIO GPLVDS mapping, a security mapping, and 2 mappings to add PCI Express for 1 or 2 ports. For the 6U overlay, the same GPIO, GPLVDS, and security mappings are defined, along with a radial aux clock ref clock mapping to add radial clocks to 6U systems. We will wrap up this video with a brief discussion of AMPs. AMPs, or the Alternative Module Profile Scheme, is a string construct that captures what exactly is implemented and supported by a plug-in card. AMP strings follow the template shown, which call out things like clock options, connector module style, depth, cooling, and pitch, and various protocols supported by the communications ports on the card. This is all defined in VITA65, but SOSA adds a few SOSA-specific elements at the end of the template. The best way to understand AMPs is to look at an example. Here we see a hypothetical plug-in card described by an AMP string. What this string tells us is that it's a 3U card based on the 14.6.11 slot profile, that it implements ref clock and aux clock with parallel terminations suitable for radial clocks, that it has a -4 connector module, which translates to a 14 SMPM module per table 13.2.11.2-2 in the technical standard, and that it is a full 160 mm depth conduction cooled with 1-inch pitch card by the -F2C parameter. At this point, it begins to describe the protocols supported by the card. Specifically, the data plane supports 40G base KR4 or 10G base KR. The expansion plane supports 2 4-lane or fat pipe PCI Express Gen 3 ports. The control plane supports 10G base KR, and the 14 SMPM connector module provides radio clocks with 8 inputs and 2 outputs. There are naturally other combinations of amp strings that are possible depending on what is implemented on a particular plug-in card, but that is a topic for another video. Thank you for watching. Please be sure to like and subscribe and watch for more videos in this series.